We'll speak about very interesting work, but counting
increasing forest.
Counting increasing forest. Everybody who is here and will behave is promised to join us for free dinner at 6:45 at Evelyn's 45 Eastern Avenue. If you'd like to join us, please let me know immediately after the talk.
Well, first of all, I would like to say Toda Rabba, and it's always a pleasure to be here talking in the seminar. It seems like it's kind of my home away from home, since I'm often in New Jersey visiting my lovely wife. So I should also mention that this is joint work with my graduate student Joshua Hallam and with Jeremey Martin from Kentucky. And if you can't read what I've written, I understand my handwriting was the only thing I failed when I was in grade school. Just ask. I'm happy to elucidate. And also, if you don't understand the mathematics, please also just ask. Hey, nice to see you. ¿Cómo estás? Muy bien. Okay, so let's start off. So overall thing for the whole lecture, all graphs are going to have vertices which are positive integers, distinct integers. So if I want to compare two vertices, I can do that because they're integers, right? So we have a linear order on the vertices. So let me tell you what increasing forests are to start off with. So a tree T is increasing, and for that I'm going to use the abbreviation just INC if the sequence of vertices on any path which starts at the minimum vertex is increasing. Right? Because the vertices are numbers. You can start at the smallest vertex in your tree, move out from it. If you always have an increasing sequence, that's called an increasing tree. So for example, that's clearly an increasing tree. These paths are kind of trivially increasing because you started at the minimum vertex after all. And this one is also clearly increasing. However, this one ain't, right? Because the one non-trivial pass out from the root goes up and then it goes down.
But you're not assuming that it's a rooted tree, necessarily.
Well, essentially you're rooting it at the minimum vertex, right? You might as well assume it's rooted at the minimum vertex without loss of generality. Other questions? Please stop me anytime you have any questions. Yes?
The numbers don't have to be consecutive either.
They don't have to be consecutive right now.
Okay.
Yes, soon we will have something with consecutive labels, but the trees may not. Other questions? Well, what's an increasing forest? Well, probably you can guess from this definition. So forest F is increasing if its component trees are. Okay, so just look at all the components, make them all increasing. So now what we're going to do is the following. So now we're going to take an arbitrary graph. So let G be a graph. And here's where we're going to go and answer Jonathan's questions. Now we're going to let the vertex set be the numbers from 1 to n, which I will usually just abbreviate as brackets n. And we're going to define f sub k for this graph. This should be actually f sub k of g, but it'll be clear what I'm working with here. To be the number of increasing spanning forests of G. Okay. So spanning, remember, just means I'm using every single vertex of G, but only some of the edges. And I'm insisting that the sum edges that I use form an increasing forest. Question?
Now, when you go to count these spanning forests,
Go ahead. Sorry, I just forgot what K was. I need to put that up.
you want to consider, like, maybe you have two forests that as graphs are the same, but then if you label them differently, then
Yes, right. Everything's labeled.
everything, all the vertices.
Everything's labeled. So isomorphism, forget isomorphism.
Okay.
Things are different when they're different.
In this data with the spanning trees, so for that definition to make sense, you're having to pick some sort of a base point at the top. Are all the trees getting choices of base points coming
Yes.
from their embedding in the graph?
Exactly. So for each tree, you take as its base point the minimum vertex of that tree in the graph.
Okay, that makes sense. Perfect sense.
Great. I like it when things make sense. Other questions? And as is usual in combinatorics, rather than studying these things on their own, we're going to turn them into a generating function. So I'm going to look IF for increasing forest of G is the generating function where we sum a certain sign times these f's of k, which we're interested in, and then for reasons which will become apparent later, instead of making this the coefficient of t to the k, we make it the coefficient of t to the n minus k. And the reasons for these conventions, as I said, this will come out in the wash. But for right now, we're just defining it. We can define it any way we like. But I think it'll be a good idea to have an example. So let's do a nice example, and let's do it here so it'll be in the middle where everybody can see it. And if I can erase, that'll be even better.
Under the computer.
Ooh, they really let me erase. Okay.
Is f sub k in OIS?
I'm sorry, what?
Is the sequence f sub k in the online encyclopedia?
Well, it can't because it would have to be for every single graph. I mean, you could do it for
Oh,
specific
you can.
graphs. This is the general, for any graph you like. So now I'm going to, let's look
Oh
at
yeah, but for some nice graphs.
Yeah, you could do that.
Yeah.
I'm happy. If somebody wants to take this and submit it, Neil is here. Talk to him afterwards. Anyway, so let's do an example. Suppose my graph is the following graph. And let's make a little chart.
So the complete graph probably is there.
They're nice for all graphs.
Yeah.
That's the point of this first part of the stuff. This is a very nice generating function, as you were about to see. Okay? So, and it doesn't matter. A complete graph, you pick your favorite graph. It will always be nice.
complete graph.
Yeah, but I want to do it for this graph because it will illustrate some things which are different. Yes?
The integers are just for leaving or negative integers is the significant for
We'll never use negative integers, so you can forget about those. Other questions?
-1.
Okay, so k equals 0. How many spanning increasing? One, right? The empty graph is clearly, right? These are all little increasing forests. What about for k equals to 1? I claim there's 4. Why?
pick an edge.
Pick an edge, any edge, right? Any edge will give you an increasing forest because you've got a minimum vertex and you've got some other vertex. End of story. So any edge. For the next one, well, there's 4 choose 2 ways of picking 2 edges, and it turns out one of them doesn't work. And this is the one that won't work. 1, 4, 2, and then 3. That's not increasing. So we have to throw that out, so that gives me a total of 5. For 3, let me just write down the 2 that there are. They are this and this. And then for 4, how many are there?
1. No, 0.
0, right? If I take all 4 edges, I've got a cycle. Can't be. So what does this increasing generating function look like? So it's going to be 1 times t to the 4th minus 4 times t cubed plus 5 times t squared minus 2 times t, no constant term. And if you're very fast on the uptake, you can factor that as t times t t minus 1 squared times t minus 2. Notice the roots are all integers. If you take an arbitrary polynomial and factor it, do you expect it to have integral roots? No. But let's put that on the back burner for a second and go back and I just want to make a little remark here, which is even though my notation doesn't encapsulate this function, if of g, depends very heavily on the labeling of the vertices. Right? So for example, let's take another graph. This is going to be my example. Well, actually, let's take g to the 1, 2. And you can make your chart and you can go through the whole thing. And when you do that, you will find out that if of g looks like, well, of course, there's still only one tree with no things. And you can still use any edge, but there are much fewer of these guys. Turns out there's only, well, much fewer. There's only 4 of them. There are none of any others. But again, this factors as, it factors again, it just doesn't factor in the same way. So the question is, what's going on here? Here's what's going on. One last definition before we state our first main theorem. So G has as its vertices 1 through n. Then for J in brackets n, we're going to let E sub j be the set of all edges ij. So these are things in my edge set where I is smaller than j. So we look at all the edges coming into j from smaller vertices. Okay. Well, let's do that here. What is E1 look like?
Nothing.
Nothing, right? 1 is the smallest vertex. There is nothing coming into E1 from the smaller vertex. E1, of course, consists of 1, 2. E3 is 2, 2, 3 rather, and then E4 is 1, 4, 2, 1, 4, 2. I think you've got the idea. Now let us take the product over all j of t minus the cardinality of these sets.
No.
And some of you already see it coming. This one gives me a t minus 0. These two both give me t minus 1. And this gives me a t minus 2. And have we seen this polynomial recently? Yes. And that is not, as I'm very fond of saying, an accident. So here's the first theorem. This is one with Josh. So let G have through n, then we always have the increasing force generating function has integral roots, and they are exactly the sizes of these edges. Let me give you a sense, with my time constraints, I can't give you a full proof, but let me give you the kernel, the main idea in the proof here. So the crucial thing that's going on here is as follows. What you want to show is that F is an increasing spanning forest of G if and only if F is obtained by picking at most one edge. From each. So, right, what I do, if I want to form an edge set for a spanning forest, I go to each EJ and I either pick one of the edges in there or not. So I can pick the 1, 2 or not. I can pick the 2, 3 or not. I can pick one of these two or not. If I do that in all possible ways, the claim is I will get all possible spanning increasing forests. But this is the generating function for the spanning increasing forests, and if you think about it for a second, this is the generating function for all ways of taking at most one element from each of the EJs. Thinking about things in terms of elementary symmetric functions, if you're familiar with those. So we're done. Once we prove this, and this, if and only it's not terribly hard. So that's the first main result. Questions? Yes?
Well, never mind. I'm going to let you go in case you
Okay. So the next thing is we're going to tell you, there are lots of beautiful graph polynomials around. Let me tell you about another one of my favorites. This is the so-called chromatic polynomial. So, we get colorful here. So, basic definition. So, a proper coloring. Oh, first of all, I should say, we've been thinking of t here as a variable. I now want to think of t as an integer. So, let t be and now we can say that a proper coloring of G is a function C, the color function, that takes each vertex and assigns it one of the first numbers 1 through t, which I'm thinking of as my colors. And this makes sense now because I'm thinking of t as a positive integer. So that's just the integers from 1 to t. And of course, the important thing for it to be proper is that if I have an edge, the color of its endpoints should not be the same. This is the usual map coloring, right? Two adjacent countries should not be the same color. And then we define the chromatic polynomial. Of G, P of G is just the number of such proper colorings. Notice this also depends upon t, obviously, even though it doesn't show up in the notation. Okay? And from this definition, it's weird to be calling it a polynomial, but let's compute an example. I think we should compute this example. So, I think this guy. So what is P of G here? Well, this graph is simple enough that I can do the following. I'll just go from vertex to vertex and color the vertices sequentially. So it's the number of ways to color vertex 1 times then the number of ways to then color vertex 2, and then times the number of ways to then color vertex 3, times the number of ways to then, right, just going to go around the graph and color each vertex. When I go to my first vertex, how many choices do I have for the color?
T.
T, right? I've got T, not for 2, but for just this color, like T possibilities for the first vertex. So that, now I've colored some color. How many colors are left for color for vertex? T minus 1, right? Because no, any color except the color I put on. Similarly for 3, I have T minus 1. And for 4, I have T minus 2, right? Because these two guys are colored differently because they've got an edge between them, and therefore I've got only T minus 2. And I'm going to ask the usual question, which is, have we seen this before?
Yes.
Yeah, but. I mean, yeah.
What?
But I mean that.
Yes. No, I'm getting to that. No. Okay, so you are already on to the next slide. The next slide says the following. Let me just finish this thought before I go to the next slide. So the next slide says, this can't always be true. Which is exactly what you're getting at. This is sometimes true, but not always true. And I can give you two good reasons, one of which is clearly, in your face on the other board. And there's another one as well. So note, this seems to be my note board. Note, P of G cannot always be IF of D for two very good reasons. One of them is that it's well known that P of G does not always factor over the integers. And if you want an example, just compute it for the 4 cycle. And you will get very non-integral roots. And we know that this guy always has integral roots. And then the second one, as you were seeing on the board, P of G does not depend on the labeling. The vertex set, where clearly the other one does. So then, of course, the question is, are they not always equal? Do we throw in the towel and go home? No! Because we are good Rutgers people. We go and find out when they're equal. So let's do that. Now, I should point out with the next definition, this is a definition which has been in the graph theory literature for a long time for other reasons, completely unrelated to increasing force. So we were a bit surprised and very pleased when it appeared almost out of nowhere in this research. But anyway, this definition may seem to be a little bit strange, but it's very useful. It's in a number of different contexts. It's what's called a perfect elimination order. So we say that G has, and no scatological jokes, please, G has a perfect elimination order. And this is too much, being ecologically minded, that's too much chalk for me to use, so I'm just going to call it a PEO. If there is an ordering of the vertex set, say V1, V2, up through Vn, with the following property. If we let Vj be the set of all Vi such that I is smaller than j and Vi Vj is an edge, then that is a clique for all. Yes, question?
From the definition, why does it follow that, since T could be one of infinitely many possibilities, why does it follow that that has to be a polynomial as it's defined?
Oh, you need to prove that. I'm just assuming. That is something that definitely needs proof, and if I have one,
Okay.
I can show you the proof after the talk.
So that's a deep matter. It's not just a concept.
No.
It's not deep.
It's
It's
an
not deep.
exercise
It
for
takes
you.
some proof, but it's not deep.
It would take you half an hour.
Okay.
Yeah, it's pretty straightforward once you see. You need something called a deletion contraction, which I haven't discussed. Once you have that in your hand, it's a trivial. Other questions? Yeah, I've totally brushed under the rug why that's always a problem, but it is. Trust me, which is why I use theory as mathematician. Anyway, okay. So this is what it means to have a perfect elimination ordering. That we have an ordering of the vertices such that if I look again, and this looks very similar to the EJ, right? If I look at all the vertices that come earlier in the order and look at the graph that those induce, that is a complete graph. Every single possible edge between these vertices. Okay, well. Let's do that here. So let's take the order, the natural order here, 1, 2, 3, 4. So, well, your V's are essentially like your E's, except that they're vertices, not edges. So V1 is going to be empty, V2 is going to consist of just the vertex 1. V3 is going to consist of the vertex 2. And V4 is going to consist of the vertices 1 and 2. And notice, this is a perfect elimination order. Empty and singletons are always cliques. These two form a clique because they are connected in the graph by the only possible edge of connection. So these are all cliques. Notice what happens in this graph. In particular, let's look at V3. What does V3 look like in this graph? 1 and 2, right? 1 and 2 are both connected to 3. Is this a clique, though? No, because 1 and 2 are not connected. Questions about this definition? No questions about this definition? I see a discussion. Are we okay? Good. So, so that's the next theorem. Again, let G have vertex set bracket n. Therefore, the increasing forest polynomial is the same as the chromatic polynomial if and only if 1, 2 up through n is a perfect elimination order for G. These two are equivalent. And even for an arbitrary graph, you can say something. Suppose, and now we're assuming what we were discussing before, that the chromatic polynomial is a polynomial in T, and we can in fact write it as a sign, some coefficient a sub k, t to the n minus k. You can always do that for any polynomial. I'm assuming also that it has degree n here. I'm going to assume things about the chromatic polynomial. I might as well assume everything I need. Then the number of spanning forests is always less than or equal to AK, where AK, for those in the know, counts broken circuits, not things that do not contain broken circuits, NBC sets. Or putting these two together, we always have this inequality with equality if and only if the ordering from 1 through n is a perfect elimination. Yes, question?
Does the chromatic polynomial ever factor into linear factors in the case where it's not equal to this other polynomial?
Yes, it does.